Alright, so as to avoid any copyright issues, which I don't think there are any issues so far with the songs I've been playing, it's just that they're going to be putting ads on my videos so that whoever owns the rights to those songs can make some money off it. But just in case, for this video, I'm going to change it up a little bit and do my own song about Kepler. And really, I'm just going to make it up on the spot, and these are the lyrics. So here we go. Kepler's third law, the periods of the... Okay, I'm done. Alright. Anyway, Kepler's third law. Last video, just to recap real quick, we did Kepler's first and second laws. First law, planets orbit in ellipses. And an ellipse is a stretched out circle. Second law, equal area for equal time. So if you orbit around and you take a look at 1 month's worth of orbit, when you're close to the star on the ellipse, you're going to orbit more slowly. You're going to go a farther distance in 1 month, but the area that this marks out in blue is still the same as when you're far away. You move faster in your orbit, so you don't quite go as far. But since the sun is farther away, this piece gets stretched out, and so these areas are equal. Third law is a little basic equation just relating how long it takes to go around the star to how far you are from the star. And that relation is p squared, which is the period, time to go around, equals the average distance to the star cubed. And for the Earth, we have nice numbers. Earth's period is 1 year, so 1 squared is 1. And the distance from the Earth to the Sun is 1 AU, 1 astronomical unit. Take a look at the other planets. Again, here's Earth, 1, 1. And if you were to, so you got to square the period and cube the distance. So you square 0.24 and you cube 0.39, and they should be pretty much right on. And so you can see these two planets are closer to the Sun. Mars is 1.5 times farther from us than the Sun, and so on and so forth. So quite a good observation by Kepler without even having a telescope. Yep. Another guy who indirectly has contributed to astronomy through physics and calculus. Basically, he just took the world by storm with his inventions. Inventing a math to explain the physics of our world. How intense is that? Inventing a math. I mean, what would it be like to meet someone like that who just, I don't know. Anyway, not many geniuses like this come along. It's not very often, you know. Once every, seems like every couple hundred years or so. And but when they do, man, they change the world. Let me tell you. He dabbled in a lot more than just calculus and physics. You know, he did a lot of. He was pretty well versed in a lot of subjects. But in terms of physics, you would have learned this in any basic physical science class. Newton's 3 laws. The first law: an object keeps the same speed unless a force acts to change the speed. So, for example, planets going around the star, a planet would just want to go in a straight line at the constant speed, but the star exerts a gravitational force and causes the planet to change direction, which is another way of changing your velocity. Newton's second law just puts that into equation form. Here's that force I was talking about, possibly the force from the sun of gravity. Here's the mass of the Earth and the acceleration of the Earth. Newton's third law: for every action there's an equal and opposite reaction. And hold on a sec. That was about a second, huh? Alright, so for every action there's an equal and opposite reaction. So if the sun pulls the earth around it, actually really the sun is pulling the earth towards it. Just so happens that the earth is moving to the side fast enough so that it never crashes into the sun. But anyway, Newton's third law is saying if the sun pulls the earth towards it, then the earth pulls the sun back towards the earth with the exact same force, and that's just in the opposite direction. So and the law of gravitation, which is one of the key fundamental laws in astronomy, because gravity is the dominant force on that size scale. Anything with a mass shares an attractive force with anything else that has mass. The smaller the masses, the weaker the gravitational force. The farther apart the masses, the weaker the gravitational force. So what that means is the Andromeda Galaxy, which is a pretty big, close galaxy, is pulling on us. In fact, our galaxies are headed towards each other. But currently they're so far away that even though that the galaxies are huge, the distance means more. It plays a larger role in the force, and so that force is weak. In fact, the distance is squared while the mass is just to the power of 1, so that really, the distance really has a much bigger role. This is that equation. We don't do math in this class again, so it's just saying the force of gravity depends on the two masses attracting each other and how far apart the two masses are. So it's pretty straightforward. And so what that means is if you have two types of elliptical orbits, you'll get two, very different. If you have elliptical orbits with two bodies, depending on the comparative mass of the two bodies, you'll have widely different orbit types. This is more like our solar system, where the sun is the center of mass of the sun and everything else is inside the star. So you can see the sun orbits around the center of mass, and also the common focus, which is different than the center of mass, and the planet orbits around too, right? Whereas if the two bodies are equal, like in a binary star system, then they both have the same size orbits around a common focus. If one of them happens to be bigger than the other, which is more typical of a binary, then I don't think, it would be a very rare chance that the stars would be the exact same mass. Anyway, you can see the larger one has a smaller orbit around the center of mass, or the common focus, I should say, than the smaller body. Also gravitationally, because the Earth is so big compared to us and our rockets, that we need, the gravitational force is pretty big, and we need a pretty high escape velocity. If we want to escape the Earth's pull, we need a pretty high velocity, 14,000 miles per hour. It's fast. This speed depends on really just how massive the object is you're trying to escape. The more I shouldn't say the bigger, the more massive it is, the faster you need to go. A black hole is supermassive, so massive that the escape speed would be faster than the speed of light, which, as you probably know, we know of no way that anything can go faster than the speed of light. So, yeah. Another thing. So, for example, the moon's going around the Earth, or the Earth's going around the sun, and we've mentioned that gravity pulls the moon towards the Earth. Why doesn't the moon crash into the Earth? And it's really because the moon has a fast enough speed. So, yeah, the moon's gonna fall. Let me do a little drawing here. The moon's gonna fall towards the Earth, but it's also gonna move that way at the same time, and so later on it's still in orbit, and it's going to fall again, but as it's falling it's going to move this way, and it stays in orbit. So that happens all the way around, and so that's how an orbiting body can stay in orbit. So if gravity were to shut off, this moon would just go straight and it would escape. That's overcoming. That's basically inertia. Gravity is keeping it in the circle, or I should say elliptical path. And this 13 slides. Um, yeah, let's talk coordinates, and we'll stop at constellations in this video. Yeah, alright. So, when you look up into the sky, you can basically see stars and a few galaxies, and we put the stars into patterns and shapes called constellations. But if you want to tell someone specifically where a certain star you're looking at is, you'll need coordinates. Just like if you want to tell someone, I'm going to meet you at this store, which is on this floor, in this mall, in this city, in this country. You give them coordinates. And same idea with objects in the sky. And so, just like on Earth, coordinates are based on the geography of the Earth. The Earth has two poles. The night sky has two celestial poles, which if you were to just take an invisible line and shoot it straight up from the poles, where it hits the sky is the north celestial pole and the south celestial pole. And that's also roughly where the star Polaris is. Celestial equator is basically you take a line from the equator and go straight out in space, and it's the equator projected on to the sky. Alright. So, just like on Earth, we have latitude and longitude, which is a very simple way to show where someone is on the planet. In the sky, we have declination and right ascension. Declination is the equivalent to latitude, and basically you go up and down on the night sky. So that would be like going up like that, or down like that. It's kind of like looking north or south. And that can go from 0 at the equator to plus 90 at the north celestial pole and minus 90 at the south celestial pole. Right ascension is just like longitude. It goes around the Earth, so it's like your different time zones, right? And of course, the Earth goes around in 24 hours, so there's a 24 hours in the right ascension, and it goes to the right if you're looking north. So you use hours, minutes, and seconds. And last slide. This is set in stone. No matter where you are, if a certain star has a certain declination and right ascension, that's the same coordinates anywhere on the planet. You just tell someone that, and they have to figure out where declination and right ascension is relative to them. But if you want to talk just local and be like, alright, look straight up, that's our zenith. If you live in a different part of the world and look straight up there, that's their zenith, which is different. Straight up is a zenith, and using the zenith and your horizon, which is kind of like the equator where you're at, but it's just basically the horizon from your point of view. So similar to declination, we have altitude. So you point to the horizon, and that's 0. And then you take your finger and you move up to straight up above you, the zenith, and that's your altitude. You start at 0 and you go up to 90. Right? And the other one, which is like right ascension, is azimuth. And you start north, you point north on the horizon, that's 0 degrees. And then you move towards the east, slide your finger along the horizon. Once you hit east, 90 degrees, south, 180 degrees, west, undo, west is 270 degrees, and back to the north is 360. So with that, going around the circle and up and down, you can locate any star anywhere on the celestial sphere. And with that, we'll stop the video, and next time we'll talk about constellations and the rest of the stuff. Talk to you later.